Bismillahirrahmanirrahim. We are going to start question number 7 of exercise 2.2, in which we are given a matrix A and we have to prove it for all positive integers n. Now, first of all, keep it in mind that positive integers start with 1 while non-negative integers start with 0, because non-negative also includes 0 but positive does not include 0. And we are given this matrix to use for our solution. Now, to prove it, we are going to use mathematical induction, and mathematical induction has two main steps, which are, first one is basis step, in which we have to prove the given equation for the first value. We have to prove this given equation for the first value. Now we know that the first value for positive integers will be 1. So we have to prove this for 1. And we have to prove it equal to this matrix, the given matrix. And then the second step is inductive step. Inductive step has two further steps. The first one is that we have to suppose that this given equation is true for n equals to k, and then we have to prove it for k plus 1. Okay, n equals to k plus 1. Now we have to prove it for k plus 1. We have to suppose that n equals k plus 1, and then we have to prove this equation for equals to this one, and using this one, because this is what we have supposed that that it comes out to be true. Now, because we have already supposed that it is true, so we have to suppose this equation. We don't have to suppose this equation to be true, rather we have to prove it to be true. We will do it and then you can get it better. First of all, we are going to write this matrix as the first step over here in our solution. X, Y, 0 and 1. Now we are going to do the basis step first. So we are going to write over here basis step, where n equals 1. Now putting this value of n in this given equation, so a raised to the power 1 equals to x raised to the power n. Here x raised to the power n will change into x raised to the power 1 because n equals 1. And then 0 remains 0 because it's a constant value, 1 remains 1, and here we also we have to suppose n equals to 1. We have to put this value of n over here, so y into x raised to the power 1 minus 1 whole divided by x minus 1. So a raised to the power 1 equals to x raised to the power 1 becomes x, 0 is 0, 1 is 1, and here we have to write it as y into x raised to the power 1 becomes x minus 1 whole divided by x minus 1. So these two cancel out and then we are only left with y. So it is equal to x remains as it is, 0, y and 1. So this we have proved it for this value n equals to 1, and now we are going to move towards the next inductive step, and we are going to suppose it for n equals to k. So inductive step, n equals to k. So now in this equation we are going to use the value of n as k. So a raised to the power k equals to x raised to the power, here x raised to the power n, so we are going to write it as x raised to the power k, 0 remains 0, 1 remains 1, and over here it becomes y into x raised to the power, here n is used, so we are going to write k minus 1 whole divided by x minus 1. So this is what we have supposed, and we are going to name it as equation 1 because we are going to use it in the next step where we are going to suppose that n equals to k plus 1. So we are going to write this value of n over here as the next step, n equals to k plus 1. Now a raised to the power k plus 1 equals to Now, as we know that a raised to the power k plus 1 will be equal to a raised to the power k dot a, because the bases are same, and when we add up the powers it becomes k plus 1 again, so it's the same. Now we are going to replace the values of a raised to the power k and the value of a matrix over here. So the matrix A raised to the power k is equal to this matrix, so we are going to copy paste it over here. X raised to the power k, then y into x raised to the power k minus 1 whole divided by x minus 1, then 0 and 1. And this matrix A is x, y, 0, 1. We are going to write it over here, x, y, 0 and 1. And now we are going to multiply these two matrices together over here. So it is equal to, for multiplication, we are going to multiply the first row with the first column. So x raised to the power k into x, we get x raised to the power k plus 1. Then plus 0 into y gives us 0, so we are not going to add it. Then for this entry, we are going to multiply the second row with the first column. So second row into the first column, we get x into y into x raised to the power k minus 1 whole divided by x minus 1, and plus 1 into y gives us y plus y. Now we for this entry we are going to multiply the first row with the second column. So x raised to the power k into 0 gives us 0, plus 0 into 1 gives us 0, so this entry will remain 0. And for this entry we are going to multiply the second row with the second column. So second row over here, when multiplied with this column, the first entry with the first one, it gives 0. This multiplied with 0 gives us 0, and 1 into 1 gives us 1. So the last two entries, 0 and 1, remain same. Now we are going to simplify it further. The first element, x raised to the power k plus 1, will be written as it is, x raised to the power, k plus 1. Then 0 and 1 remain same. Now we are going to solve this thing. We are going to take x minus 1 as the LCM, so y will also be multiplied with x minus 1. So xy into x raised to the power k minus 1 plus y into x minus 1 whole divided by x minus 1 is equals to x raised to the power k plus 1, then xy into, we are going to multiply x inside the brackets and then take y as a common from both of these terms. So y into x raised to the power k into x gives us x raised to the power k plus 1. Then minus x into 1 gives us x minus x, plus, now y is taken as common over here, whole common. So we are going to write just what's in the bracket over here, plus x minus 1 whole divided by x minus 1. And then 1 as the last entry, 0 over here is equals to. Now both of these terms cancel each other, minus x and plus x, and we are left with y into x raised to the power. Okay, first of all, the first element is x raised to the power k plus 1, then 0 and 1 remain same. And then over here, y into x raised to the power k plus 1 remains as it is. These two are cancelled, and then we are left with minus 1 whole divided by x minus 1. And we have proved it because as you can see, this is one side, we can call it left hand side. We are calling it left hand side because as we see in the question over here, that we have solved this side. Now we are going to put the value of n equals to k plus 1 over here. We have solved this one but not this one. Now we are going to solve this side. So we are going to write it as a raised to the power k plus 1 equals to x raised to the power n and 0. We are going to write it over here, x raised to the power n 0, and then y into x raised to the power n minus 1 whole divided by x minus 1, y into x raised to the power n minus 1 whole divided by x minus 1 and 1. Now we are going to put the value of n as equals to k plus 1, n equals to k plus 1. A raised to the power k plus 1 equals to x raised to the power n equals k plus 1. So we are going to replace it over here. 0 and 1 remain same, and then y into x raised to the power k plus 1 minus 1 whole divided by x minus 1. So this is our right hand side. Both these hand sides are equal, so we can say that we have proved it. Nice. Again, in the next part number 2, we are given with the matrix A and we have to prove it for all positive integers n for the given variable matrix. So first of all, we are going to write the matrix A over here as the first step. A equals, and the matrix A is 3, 1, minus 4 and minus 1. Now the first step is called basis step. Basis step where n equals 1. Now we are going to put this value of n over here in this given equation. So a raised to the power n becomes 1. A raised to the power 1 equals to 1 plus 2 into n. 2 into 1 gives us 2. Then n is equals to 1 over here. This n becomes 1 over here. Then minus 4 into n. Minus 4 into 1 gives us minus 4. And then 1 minus 2 into 1 gives us 2. So a raised to the power 1 equals 1 plus 2 gives us 3. 1 remains same. Then minus 4 remains same. And then 1 minus 2 gives us minus 1. So this part of on the basis step is equal to the given A matrix. So the first step is over. Now we are going to move towards the inductive step. As the first sub-step of inductive step, we are going to suppose that n equals to k. And we are going to put this value of n over here in this given n matrix. So a raised to the power n becomes k equals to, we are just going to replace this n with k. So 1 plus 2k, then minus 4k, then this n also becomes k, and then 1 minus 2k. Now a raised to the power k equals, okay, now we cannot solve it further, so we are not going to write a raised to the power k over here. Now the next step of inductive step is, sub-step of inductive step is n equals to k plus 1, and we have to prove it for that value. N equals to k plus 1. So here a raised to the power k plus 1 equals a raised to the power k dot a. We are going to write a raised to the power k plus 1 over here, and then we are going to multiply these two equations over here. So a raised to the power k plus 1 equals, we are just going to replace the value of n over here by k plus 1. So here we are going to write 1 plus 2 into k plus 1. Then this entry becomes minus 4 into n is k plus 1. So we are going to write minus 4 into k plus 1. Then for the next step, it's just n. So we are just going to write over here k plus 1. And then here it is 1 minus 2 into n. So 1 minus 2 into k plus 1. Now it is equal to a raised to the power k dot a. So we are going to write the value of a raised to the power k, this whole matrix over here. 1 plus 2k, k minus 4k, and then 1 minus 2k. And this matrix is multiplied with a, which is given over here. So we are going to write it over here next to it. And it becomes 3, 1, minus 4, and minus 1. Now we are going to open up all these brackets over here. So 1 plus 2k plus 2. Then the next element would be minus 4k minus 4. Then this entry would become k plus 1 as it is. And then this would become 1 minus 2k minus 2 equals, now we are going to multiply these two matrices together. So first of all, we are going to multiply the first row with the first column. So this multiplied with this becomes 3 into 1 plus 2k plus 1 into minus 4k gives us minus 4k. Then this entry would become the second row multiplied with the first column. So 3k plus 1 minus 2k. This entry would become the first row multiplied with the second column. So we get minus 4 into 1 plus 2k. And then minus 1 into minus 4k gives us plus 4k. And then we are going to multiply the last row with the last column. So we get minus 4k minus 1 into 1 minus 2k. Let it remain over there. Now solving this side further, we get 2k plus 2 plus 1 gives us 3. This entry remains same, k plus 1. There's nothing to solve over here. And then this also remains the same, minus 4k minus 4. Oops. And then this entry will become minus 2k. And then minus 2 plus 1 gives us minus 1 equals to, the first entry would become 3 plus 6k minus 4k. Then 3k minus 2k gives us k plus 1 remains same. And then minus 4 into this entry would become minus 4 minus 8k plus 4k. And then minus 4k minus 1 into this value gives us 1 plus 2k. Now the next step will be, this whole matrix will remain same because there is nothing more to simplify. Now we are going to simplify this side. So 6k minus 4k gives us 2k and plus 3 remains same. Now this whole entry remains the same, k plus 1. This entry will become minus 8k plus 4k gives us minus 4k. And then this minus 4 remains same. This minus is not visible. Okay, minus 4k plus 2k gives us minus 2k, and then this minus 1 remains same. Now as you know that left hand side equals right hand side, so we have proved it also. Yoo-hoo! Thank you so much.